about library parameterized modules or the LPM modules that is provided by Quartus. So these LPM modules are nothing but the logic blocks that are being provided by Quartus so that you can use it in your programs. This basically means it's trying to make your life easier so that you can use the pre-generated blocks that are provided by Quartus. So yeah, me just and today I'll be using the multiplier block provided by Quartus. So the special the special feature of this LPM module which provides advantage over the regular blocks that we actually created. You can optimize it basically for area or speed, which are two important parameters in any digital design. So let me just show it to you. This is the IP catalog, and here you have so many functions or the mod or the functional blocks that you could use. And if you get in here and arithmetic, as you can see, there are a lot of pre-built logic blocks like complex multiplier, converter, comparator, and other blocks as you can see. So I'll be using the multiplier block. So what you do is you start off with this. What do you want the name of your multiplier to be? So let me just give it as mult and the type of file you'd want it in, and once you press OK, it'll show this window should pop up. This basically is the interface where you can configure your multiplier. As you can see, this will be the data A, data B, and your result. This will be, this is just a visual representation of the block. Now here, as you can see, there are a few options where multiply data A with data B input, which means data A and data B will be two different, or you can multiply data A by data A in itself. This is one of the option. Now you can fit the size of your multiplier and multiplicand over here, and this will be the resultant bits. So 8 into 8 by 8 multiplier would give you 16 bits. So this is automatically set, or else if you want to take select the bits, you could also do that by selecting here and the number of bits that you'd want. So this is the board that I'm using, so cyclone 5. Now if you go to the next stage, you can see some more options. So you can also set a constant value or a pre-mediated value to one of the inputs. So you could do that here. If you want, you could set the value here, else you could just let it go. And you can do a signed or unsigned multiplication, which is also an important, and this is in what way you can implement your multiplier. And here will be the important part. So you can actually pipeline to make your multiplier work faster, or the stages you could pipeline your multiplier. And here is the other way to optimize your design. There are three options where you can, as you can see, it's default, speed, or area. You can choose this based on your preference, so you can optimize your multiplier for speed or area. So yeah, this is an interesting option which basically gives an edge over us creating our own modules. Here, as you can see, once you generate this, you'd also need to generate the netlist so that you could use it in your modules. So you gotta get this, and then in a summary you can see there are a variety of files that will be generated once you click OK. So let me just go through this. This is a .v file, basically the very long hardware description of your file, and these is AHDL component and the VHDL component, which I won't be using. So this .bsf file is basically a schematic representation of the block, or the block symbol file. Basically you would use this in schematic entry, where you can usually place it on a schematic. You'll get the multiplier block by itself, and you can use it and connect it by wire. So that is the BSF file. Underscore instantiation file is basically this basically will have the information about the ports, so that you can instantiate or get it into your own program or your own module. Like if you want to use your multiplier in some other module, or if you're considering building an ALU and if you want to call that multiplier module, so you'd use this would basically provide the information. And this underscore VB is the black box, or this is another file which basically contains just the input and output ports. This is basically like a black box, which this is a reference for Quartus, so that it knows that a file called multiplier basically exists during synthesis. So it's a reference for Quartus to synthesize, and it knows that there's a block called multi. So that is this, and this is an important synthesis file. This basically contains how you'd map this multiplier on FPGA. This basically contains every information about what you'd need while you're mapping this multiplier onto your FPGA. So this is the default. You couldn't select this, and these are few other options that you could select. So since I've already generated, I won't be doing this. So now I've generated a 4 by 4 unsigned multiplier. As you can see, once you generate the .v file, you can see here, this is the description of your module. You could see the data A and data B being 4 bits and the result being 8 bits. This is the asynchronous clock, which is put to 0, and this is a clock enable, which is put to 1. Basically, these are not used, and this clock provided by multiplier is set to 0, and this is sum and some other clear. So yeah, synchronous clear and asynchronous clear. So these are just more available options which we are not using as of now. So here will be the definition of a multiplier. As you can see, since I chose this in default, this is leaning more towards speed. So as you can see, this is quantized to speed as 5, and the type of multiplication I'll be doing is unsigned. So it says unsigned here, and the block that I'm using, LPM underscore mult, and the width of multiplier and the multiplication and the product. So this is the definition of your block, and these are some of the other files that have been generated. This basically gives information to the quarters tool, saying how it was synthesized or how this multiplier block was synthesized, like what are the conditions that you gave while synthesizing this block. As you can see, auto size result numeric 1, this basically means it automatically selected the product bits as 8. As when you do 4 by 4 multiplication, you get it as 8, so it automatically set it to 8. And as you can see, there are so many other you know information here. As you can see, width of A, B and P, and clock enable being set to 0, and this block being you know built for speed or optimized for speed. Although it's default, it is slightly leaning towards speed. The type of multiplication unsigned. As you can see, this says that data A is of 4 bits, data B is of 4 bits, and it doesn't have any constant values, So this part of the code basically contains all the, you could say the constraint or the conditions with which we built our multiplier. So this is how it goes. And here I've created a test bench for the same, where you can see for every 10 nanosecond interval, I've given these conditions, and after this 40 nanoseconds, I've used the repeat function to basically generate random numbers from 0 to 15. So this is the test bench that I'll be using. Now let me show you how it will look once it's being, synthesized. As you can see, I've already went ahead and synthesized the program or the multiplier module. So this would be the RTL view of the block. As you can see, it's just another multiplier. Since this is a pre-built block, it has the data in and data input, two data inputs and the output, and the other asynchronous clear and the other options that you could have. If I zoom in, it's the same, it's just the block. If I go deeper, you can see that the decoder and how, basically the multiplier is built for speed 5. It is a quantifiable thing of 5. So yeah, for a maximum speed of 5, this is how it would look, your multiplier would look. So that's the idea here. And then let me go ahead and show you post fitting. Here we got the data input and output, and our output here, and this is the block. Here I could just go here and show how it would look, chip planner, so that we could see how actually it's been utilized. This would be our FPGA, and this is all the blocks that are available, and all the other separate PLLs and all the extra blocks that has been provided with an FPGA. As you can see, this block here is shown in red because this is where our multiplier is being utilized. So if you want to have a deeper look, you could just double press and As you can clearly see, based on the Cyclone 5 architecture, how our multiplier is being, implemented on the FPGA, or what are the pin ports that you could use. So yeah, you can have a detailed analysis of the same. So yeah, as you can see, it's been implemented in this single block. And now let me show you. Let us look into the filter and how many cells that have been used here. So as we look at the resource usage summary, you can see it uses 9 ALMs and 18 ALUTs. So this is how much it uses to implement it on an FPGA. And then there are 16 pins, 4 4 for data A, 4 for data B, and 8 for product. So 16. And since we are not using clock or any of the other pins, it isn't shown here. And these are, as you can see, the any other blocks are not being used, and the memory block is also not being used, so it's been shown 0, and number of DSP blocks is 0. So yeah, as you can see, the key takeaway here is you can see we are using 9 ALMs and 18 ALUTs. Now let us deep dive into timing analyzer and look at the timing report what we've generated here. Let's open the timing analyzer. Here I have the timing analyzer. Let me read the netlist. Having read that SDC file, you could see here we have the report for the same, and if I try to arrange it in descending order, you can see this is the difference here. The key difference is this is basically a purely combinational, when you take a purely combinational circuit into consideration, this is what you get. And as you can see, this is register to register, register, so flip flop to register, and flip flop to flip flop. So these are basically, what you could say, the virtual registers or pseudo registers that have been created so that you could get approximate timing values. So as you can see, from input port data A2 to output port result 4, it would take the longest time. So this could be used as Fmax. So this is one of the ways you could calculate, or if you want it to be more clear or get the Fmax more accurately, you could always use this wrapper module. So this is another technique where we are deliberately, generating registers at the end of each output. As you can see, I generated result register at every output, and at every positive edge of clock, it basically the register that I've generated captures the output. So this will be more accurate as it is not a virtual or a pseudo register. We are actually creating the registers, and to know the accurate timing, you would always measure the time from a flip flop to another flip flop to get more accurate results. So yeah, this is another way to calculate more accurate results if you'd want. So now let us go and simulate the same. Let's hold on until the simulator turns up. The workspace is empty. Now let's go ahead and compile the program. Go to work. As you can see, it already has the main module and the multiplier module. So what you got to do is, got to go, you not only have to compile your test bench, but since you are using LPM modules or the pre-built logic modules from that is provided by Quartus, you also have to compile this 220 model, because this basically contains all the timing information, or basically every information that you would want about the LPM module. So you got to compile this too. As you can see, it compiles basically every LPM module that is present in that 220 model. That's when you could simulate your actual file. So let's go ahead and simulate this. Uh, As you can see, I've simulated my design, and you could also see the result here. Since I used the $display function, you could see all the multiplication being happened here. Could also observe it on the wave. Okay, more clear. As you can see, I have the multiplication values here. Let's go ahead and change the regex so that it's easier to understand. As you can see, the multiplication is correct. I basically used these 4 cases, and the rest of the cases are the random cases or the random numbers that have been generated from my test bench module. So I'll go ahead and convert this back into binary so that I could show it more accurately when I'm implementing it on an FPGA. So having done this, as you could see, the simulation has been successful. Let me just go ahead and dump the program. Now I've already configured the pins that would be required. So as you can see, I've already configured the pins. The first 4 pins from the left will be for data A, and the right extreme would be for data B. And here I'll have the LED results. So having done that, you'll gotta recompile again, and since I'm already done with that, let me just go ahead and open the program device. Let's choose the port that we are using. Add the file. Having added, this is the board. So this, and let me just go ahead and dump the file onto the FPGA. As you can see, it's completely done. It's been implemented. Now I'll be showing the output on the FPGA. Thank you.
So now I'll be implementing few of the cases that I used in my test bench. So here I have all zeros. Now let me just multiply. This 4 bits would be A and the last 4 bits would be B. So let me just go ahead and multiply 3 and 5 just like in my test bench. As you can see, it's 4 ones, which means 15. Now I'll be simulating 7 into 9, which is 63. So this would be 7, this would be 9. So this is 7 into 9. As you can see, it's 0 0 and rest of them are ones, which is 63. Let me just go to the extreme case of 15 into 15, which is 225, which is basically 3 zeros, 4 ones, and followed by a 1 at the end.